Hi, we are going to look at the schedulability of periodic tasks in real-time systems using the UB test and the exact schedulability test. So first we have this idea of a periodic task. A periodic task has a certain amount of execution time and a period in which it occurs. In rate monotonic scheduling, we denote the priority of these tasks with a subscript. So a lower value is going to be a higher priority, and we can attach this either to the task itself or some property of the task. Our problem right now in particular, however, is if we're given a collection of these periodic tasks with C and P values, can we schedule them with them all meeting their deadlines of their periods? So to do this, there's a general workflow. We first use what's called the utilization bound test. And it's quick and dirty, and the nice thing is that if you pass it, you're done, you're schedulable. If you don't pass it, that does not mean you are unschedulable, however. You use what's called the exact schedulability test after that. It is more involved than the utilization bound test because you must do a test on every single individual task. However, you will know that if any task fails the ES, it will not be schedulable. Likewise, if every task passes the exact schedulability test, we will be schedulable. So first let's go through the UB test because it is simpler and it's often what you do first. We have this idea of what's called utilization. And in order to find the utilization of all of your tasks, all you do is you take the sum of the ratios of the execution time over the periods. So task 1's execution over task 1's period, and then you sum that with task 2's execution time over task 2's period, and so on and so forth. This will then give you a value of your utilization. There is a bound called the L&L bound given by the right here, and a task of common values based on n, that so long as your utilization is below or equal to it, you're schedulable with your task set. Like we said before, however, if you go above this and you don't pass, that does not mean you're not schedulable. You just have to do the exact schedulability test. And that test, once again, you must do it on every task. But there are two parts to each of this task, getting R0 and iterating past that. These are very stupidly long formulas. Not even long, they're just convoluted. Lots of subscripts and superscripts. You iterate until an R value is greater than the period, or you go until the R value does not change and that value is less than or equal to the period of a given task. I think it's easier to just show an example of it being worked out and it'll make a lot more sense. So I like to use a table where you have rows for each task and columns of information. You have 3 columns for information about your tasks, and we'll list them out right now, why not? Task 1 has an execution of 4 and a period of 10. Task 2, an execution of 6.1 and a period of 14. Task 3, 1, and 70. With this set in mind, can we schedule all of these tasks? So the first thing to do is to get an R0 value for the first task. We always want to start with the highest priority task because if any of these tasks fails along the way, then we are not schedulable. So the first thing to do is to find the R0 of a given task. Now to do that, we use this formula here, and all this means is sum up the execution times of all higher priority tasks up until that task. So for the highest priority task of R0, that's real easy. It's just 4, its own execution time. To get later R values, what you then do is you take the execution of the task you are testing and you sum that with a summation of the previous R value divided by the period of any higher priority tasks. There are no higher priority tasks in this one, so it's actually going to be 4 again. So because we have the same value in 2 sets of R, and that is less than the period of itself, we know that this first task is schedulable, which is intuitively, it makes sense because C of 4 is less than the period of 10. So if we were to only have the first task, we're fine. For the second task, it takes a little bit more work. To get the R0 value, it's also quite simple. You just sum the C values of the first and second, which will give you a 10.1. After you do that, to get your R1 value, you take that 10.1 and you divide it by the period of the higher priority task. You take that division and you take the ceiling of it. So in this case, 10.1 divided by 10, and the ceiling of that is going to be 2. You then multiply it by the execution of the given task. So 10.1 divided by 10, rounded up to 2, multiplied by 4, so 8. So you have 8, then plus the execution of that task, 6.1, and you get 14.1 for your R1 value for the second task. As we can see, this value is actually greater than the period of the second task. So this means our task set is actually not schedulable. We're actually done now, and we can say that it is not schedulable because of that value. For the sake of exercise, however, let's also calculate it for the third task, because why not? I'm going to work a little bit faster here, but feel free to pause along the way. So the R0 value of the third task is just the R0 of the previous value plus the execution of that third task, which is 1, giving you 11.1. 11.1 divided by 10, rounded up, is 2. Times 4, that's 8. And then you do the same with the second task. 11.1 divided by 14 rounded up, that's 1, times 6.1. So 8 plus 6.1 plus 1 gives you 15.1. Then you use 15.1, divide that by 10, that's also 2, gives you times 4, 8. And then you do the same thing here, only now 14, 15.1 divided by 14, that rounds up to 2, giving you 12.2. So in the end, it ends up adding up to 21.2. And then if you use 21.2, that also increases on this value, giving you 25.2. And then if you do the next value, it's 25.2 again. And this is why it's actually important for you to test every single task. Even though this 25.2 is less than the period for task 3, and task 3 is schedulable, because task 2 is not schedulable, our entire task set does not work. Some patterns that you can notice. If a previous R value goes over a multiple of P than the previous one, then there's going to be a different value. For example, 15.1 is going to give you a ceiling division of 2 on this, but 21.2 is going to give you a ceiling division of 3. So if you look at the chart, you can very easily see when you are going to exceed a period value and when you are going to have to add in another execution time. So all of those concepts held together, the UB test, the exact schedulability test, these will let you determine if a task set can be schedulable under a rate monotonic setup. This doesn't take into account things like blocking time or switching time, but this is a good start. Thank you.